Hello, sorry, we are a little bit late today. I had some problems myself in my computer, so I had to restart, and so we have already accumulated a few minutes delay. I just wanted to welcome everyone today here in this Present Sinter free webinar. Personally, it's the last webinar for me this year in 2020 of this series, the free webinars. I hope you have had the chance to follow also the other ones. There will be another one on hard materials in December. I hope you can enjoy this. I can tell you we had about 200 registrants. I don't know how many we will be in the meeting, because for a free webinar sometimes the participation is then lower than the registration, but we have already about 80 people here today, so I think it's an interesting day today. And I would like to start with one thing that we are doing these days in the webinars, that is starting with a short poll. And I would like to invite you to go to, if you can see my slides, now to go to Slido, which is this tool for polling, and so that you can also scan the QR code on the screen if you have your smartphone. It works. We will do an anonymous poll in this tool. So let me start the poll. If you manage to go there, please use that code PSW00. I hope you have joined it, and we have just some questions for you, just to understand what is your background. I hope you can take part in the poll, and I will share also the results while they're coming. Let me change the slide that I'm sharing. Takes a while. Yeah, some answers are coming. I hope you can all join www.slido.com and join that. So we have already 22 answers, but you are many more than that. So please do go there and give us some feedback about your background. So many of you are manufacturing, studying present sinter, either parts or powders. So you already probably know something about that. But there are just some people that are joining to learn something about present sinter. Please go to slido.com and join this poll. We have some more also later for you. Not much. We're not bothering you too much, but just at the start and at the end we will some more questions. Please keep your mic shut, please. We hear noise. Thank you. Yeah, I'll wait just a few seconds to see if we can get some more. Yeah, so basically, as I said, we had about 200 registered people from all over the world. I don't know if we have friends from the countries that I've seen in the registrations, like Malaysia or the African countries or Brazil, of course, US, Canada, and all of Europe. Basically, it's all over the world, Australia. So thank you for joining this event again. We will see next year if we can run again some free webinars. Maybe not as much as this year, but we all hope to be able to run events in person next year. So Okay, so we have about 50 answers. Most of you already know something about present sinter, so that's also interesting for our speakers. Let me go to the second question. And so again, it's linked to this. How much do you know about present sinter? So just to see if you can give us some further feedback on that. Yeah. Yeah, so of course, as the percentage was what you've seen in the first question, this is more or less similar, but at least all of you already knew about present sinter, at least the name. Oh, not that. Okay, so please keep your microphone closed, please. Okay. Yeah. So again, more or less the same sketch that we had from the first question. Okay, as we have already spent some time, let me go already to the third question, which is, you are interested in some applications. What are they? Of course, we have just listed the most important markets for present sinter, automotive, of course. Yeah, it's interesting to see what is your background, but also what are your expectations about that technology. So again, interesting for the speakers. It will be interesting, of course, to learn what are the other applications, but alas, we have no time to go in that detail. Still, it's interesting, and well, it's not just automotive, as sometimes people think. Present sinter is okay, of course, mainly automotive, but it's not just automotive. Okay, so yeah, having seen this, I think we can go back to the main agenda, which is, as you already know, a list of speakers. I unfortunately will have to give you the first part of the seminar, which is something we do in all seminars, so a short presentation of what is EPMA and what we do in the field of present sinter. So let me share the other slides. Today it's a bit complicated, I'm sorry, but I hope we can get better with time. Okay, so this was already shown. As I said, first presentation, EPMA activity in present sinter. I will take you not more than 10 minutes, I hope. What we are, there are many people who are not members here, so maybe I can spend a few words here. We are the European Powder Metallurgy Association. We were formed more than 30 years ago. We celebrated last year in Brussels. Our main office is in Chantilly in France. And we want to promote, develop, and represent the European PM community everywhere it is possible. Of course, promoting powder metallurgy as a whole and developing its future in the world and not only in Europe, if possible. Of course, we are made up of our members, and the members decide what are the activities of EPMA. And the technical activity of the association is actually exercised in these groups. We depict the powder metallurgy as a tree, which is actually growing from the powders that you see at the bottom, ferrous, non-ferrous, and it develops into branches. And of course, we have branches for the most important processes in powder metallurgy: present sinter, metal injection molding, hot isostatic pressing, additive manufacturing, which is one of the latest additions in our groups. And we also have groups on materials like the hard materials group and the functional materials group, which is actually the latest group introduced. Press and Sinter was there from the start because, of course, this is the main technology that originated all the
Bruno, we can hear you.
Bruno, you are on mute. I don't know how this happened.
Bruno, you are on mute. You are with
Can you hear me now?
Now, yes.
Yeah, sorry, I don't know why it happened. I don't know where it lost me. Nevertheless, this is the powder metallurgy tree and all the groups that are in EPMA, the sectoral groups, and which convey most of the technical work in the association. We do the meetings, we do surveys and statistics within the sectors. We organize seminars or webinars like this one. We publish publications to promote the technology, and we try to foster research and development in the sectors. We also have working groups which are dealing with environment, health, quality, and safety, like the EHQS. So standardization issues, sustainability, and chemical issues. We also have a group of the main academician or academical groups in Europe, and they help us in this EPMI, European Powder Metallurgy Institute group, to organize the trainings, the education, and to support the EPMA in creating the content for the Congress, for instance, and the seminars. So going back to the Europress and Sinter group, which is what is organizing these webinars today as well. This was already there from the start. It had a different name in the past. We organized seminars. You can see some pictures here from the latest seminars. We will have another seminar in just 1 month, and I will go to that in a few seconds. There is a publication that is free to download on our website, which is an introduction to press and sinter technology, which would go in parallel with this webinar, more or less. You can find much of what will be said today also in this publication, and we do the statistics, as I said, which are for the members and the participants. Activities that we have run in 2020, there were 2 special interest seminars in our Congress that were even on 3 sessions, so 1 on sustainability and 2 on modeling of press and sinter. And we also had 5 technical sessions in our virtual Congress that was held 1 month ago. We had a sectoral group virtual meeting last week, and we had this webinar today. And also we will have the seminar, as I mentioned, we will have this seminar in 1 month. It is focused on electrification and the opportunities for powder metallurgy, not only the threats to powder metallurgy coming from electrification, but also the opportunities. It will be a virtual event again, so please go and check on our website, on our seminar website, all the details. In 2021, we already plan, of course, to have a Congress next year, hopefully in Lisbon in person, with, again, special interest seminars, technical sessions, and probably the meeting there. We are also preparing a showcase in one of the main OEMs, automotive OEMs of PM parts next year. We hope we can make it. It's still to be confirmed. We will also have a PM live course on press and sinter, which is a detailed course. It will be partly virtual and partly in Trento, and maybe Alberto will confirm later. We might organize other webinars next year, so please stay tuned. So to summarize again, this is what is happening until the end of the year, and you can see a lot all other events as well. But please make a note for the 8th of December and go check our seminars EPMA.com website for registration. It's also not so expensive, so please take a look at that. And again, next year you can make a note of probably this is what is already decided. We will have more events, but these are already more or less confirmed. And make a note of the EPMA Summer School in July if you want to have an introduction to the whole of powder metallurgy. So to finalize my talk, projects, as I said, we want to foster research and development. Club projects within EPMA are for members, but member companies join in a small consortium and they finance a small research activity which can run over a few months or just 1 or 2 years maybe. And it's very popular. You already had about 30 projects like this, and Press and Sinter is one of the sectors where these projects are really working very well, and we already have 2 running, and we might have 2 more next year. So we will wait for you. If you are a member, of course, you can join these without any problems. And also we do funded projects. I must mention we are working in a project which is called Supreme, where we are at the end. It will finish at the end of the year. And for this, I would like also to help us and go and join this survey on the environmental impact of powder metallurgy. Is not for experts. It's not for experts of sustainability or environmental impact. It's for everyone in the industry, and it's for everyone everywhere. So please find this survey if you want to give your opinion on the impact indicators. What are the most important impact indicators for powder metallurgy? It's a sort of sketch that we want to screenshot of what we feel in the industry, and it's not intended to be for experts only. So please help us in this project. So this is what I wanted to say. I hope the start was not too terrible because we had a lot of technical problems, but I think we made it. And so now I would like to give the floor to our first presenter. So not me, but José Manuel Alba from Universidad Carlos III de Madrid. And I hope he can give you his presentation without the problems that I had. Thank you very much.
So good morning, everybody. I think you can hear me properly.
Yes, we do.
So first of all, thank you, Bruno, to EPMA for inviting me to give this short presentation about the fundamentals of press and sintering. It's really fundamentals because I have just only 20 minutes to explain more or less what this technology is in general way. So I would like to start just to remember what is powder metallurgy. Press and sinter is just in the middle of this technology, which is called powder metallurgy, which is a materials forming technology based in the production of metallic or other materials from powders through a process called sintering. In the middle of this, there is a lot of different field of applications of powder metallurgy. The first one is application with high cost savings, with large manufacturing series, complex shapes, small side parts. In this case, we don't have an improvement in properties in general, but we are taking the advantage of the cost, the precision, and the productivity. This is maybe the main field of application in which press and sintering works better. So one example is one part produced by press and sinter, which is the synchronizer hub for the automotive industry. This is one of the examples in which we can see the advantage of the profit of this technology in terms of precision, in terms of cost, and the relationship in between the properties and the cost. So this is the first approach to the automotive industry, because press and sintering in some way is surrounding the automotive industry through the development of the PM steels during the last, let's say, 90 years. So the first part was introduced in 1937, and it was a pump oil year manufactured by General Motors. But it was not the first. During these last 90 years, it was developed more than 100 different parts, all of them manufactured by press and sintering. And in this slide, in the next one, I can summarize some of the typical parts that we can find in a car. So press and sintering has been introduced through the PM steels in a lot of systems in the car, like car transmissions. We have not only the synchronized hub, also synchronized ring and others. In the car steering, through the shock absorber, which is the most, let's say, famous part made for this system of the car. In the engine, and many other parts like widescreen wiper drivers or air conditioning compressor cylinders and rotor. So the second important field of applications for PM is those applications in which we can obtain higher properties performance rate, usually with higher properties than any other alternative manufacturing process. Usually by press and sintering, we don't feel these kind of applications, but also sometimes we can find applications that can fulfill this statement. And the third one is those cases in which the powder metallurgy is the unique way. So we can say that this is the captive, it's a captive technology, because the powder metallurgy is only the unique way that we can produce the specific part. So if we combine these three fields of applications, we can find the ideal applications should fulfill first good price. Second, sometimes it's the unique way to do it, and sometimes we can get the better properties that we can be obtained by this specific application. In the case, we can find by press and sintering two typical applications in which we fulfill the three fields of applications. One case is the cemented carbides, the hard metals, and the other case is the cell lubricating bearings. In those cases, by press and sintering, we can get optimal properties. We can get, of course, a good relation between cost, precision, productivity, and in these two specific cases is more or less the unique way to obtain. Of course, cemented carbide can be obtained by hot exotic pressing or plasma sintering, but cell lubricating bearings, the unique way to obtain is by press and sinter. So also the history of cemented carbides and bearings are really all in relation with press and sintering. The first hard metals products produced by press and sinter was developed in the early 20s, and the bearings were also developed in the first 30s. I have to say that at least in Spain, and I think in most part of Europe, most of the PM companies that now are successful companies producing PM steels and other powder metallurgy products started in the early 30s, 40s producing bearings made by bronze and copper-based materials. So this is the typical application in which it's not so difficult to manufacture. It's difficult, but not so difficult. It's just press and sinter in that case, and you can reach a really interesting material that can be obtained by any other alternative method. So maybe we can say that cemented carbides, hard metals, cell lubricating bearings, and PM steels are the core of the PM industry in some way, and are also the three methods, the three kind of materials that can be produced by press and sintering in more extent. At the end of this short presentation, I will show you a breakdown of the market, and you will see how these three kind of families of materials cover most of the production of the PM materials in the world. So we can, in this slide, we can have a look to the complete technology from the starting point in which we have to produce powders. We have to adapt the powders to the next step, which is the pressing process. Then we have to go to the next step, which is sintering. And many times after sintering, we have finished the process because we don't need any other finishing operation. We have the material ready to be used in the application. But sometimes after sintering, we have to produce some special fine finishing operations like sizing, impregnation, and of course, in the case of steels and other materials, heat treatments, like any other conventional processing method. Starting from the beginning, we have to produce powders, and we have to produce powders of many different different materials. We have, for instance, we have in the case of steels, alloying elements such as is the copper, and we have to produce these materials by different powder production methods. Some of those methods are chemical methods, like the electrolytical ones, typical for the copper powders, but also Carbonyl process, in which we can obtain very rounded and small powders, in that case for nickel. We have another kind of chemical methods, like the sponge iron process, which is a solid state method to produce pure iron powders. In this case, this is a picture from the Hoganas process, in which we mix the iron ore with a high level of content of iron, in that case in the order of 70–75% of iron. We mix it with some materials like coke or limestone to reduce and to produce some to eliminate the impurities of the iron ore. And at the end of a very long furnace, in which we produce the reduction process and nearly to 1200 degrees in solid state, we develop this sponge iron powder, which is quite interesting for the present sintering process. Another method is the well-known water atomized powder, water atomized system, in which we obtain atomizing the melted liquid iron in order to produce these rounded particles that could be also very interesting for the present sintering method. Of course, we can produce powders also for gas atomization, but gas atomization method produce spherical powders, usually fine powders that are not usually suitable for the present sintering method. Because for present sintering, we need to fulfill specific properties to have a good process, a good advantage of the process. So we can have many different powders with different shapes, with different price, of course, but not all of them are suitable for the present sintering method. If we analyze the properties that we can find in a powder, in a particle, which of those properties are interesting we have to adjust to have a good process in present sintering. Of course, flowability, because we have to fit a die in a very speed way. We need to have a good compressibility, so that means the powder should be not so hard in terms of in order to allow the compressibility. We have to have an appropriate size and size distribution. Sometimes size is highly related. Most of the time, size is highly related with the flowability and other properties, the apparent density, for instance, and also we have to have an appropriate shape. For this reason, some shapes like for instance flakes or not rounded shapes are not suitable for the present sintering method. In the iron and the low alloy steels industry, the most used powders are the water atomized iron powder and the sponge iron, because they fulfill all the good properties that we need for this method. Good flowability, good compressibility, because are pure iron powders. We have the proper size to assure a good flowability and a good apparent density. And in that sense, the problem is that we have to introduce the alloying elements, and if we use fully prealloyed powders, the hardness of the powder increases so much, and the compressibility is affected. For this reason, we used to admix the powders with the alloying element, the iron plane powders with the alloying elements powders, or we can try to find other alternatives, like the development of prealloyed powders or diffusion alloyed powders that can maintain the homogeneity of the mix, but avoid to lose the compressibility. So once we have the powder ready to be pressed, we have to go to the next step, which is pressing. Pressing is uniaxial pressing. That means that we fill a die with the powder and we apply the press with punches, usually from the bottom and from the top part. The most easy process is the so-called simple effect uniaxial pressing, in which we apply the press from the top part of the die. In that case, the problem is that the density inside the green part, inside the part after the pressing, is non-homogeneous, because usually the density near to the punch in which we are applying the pressure is higher than in the opposite side of the die. So we can adjust this problem using the so-called double effect. If we apply pressure from the bottom and from the top, we homogenize a little bit more the density, and we have only a line of lower density in the middle of the part. And also we can improve this using what is extremely normal in the industry, is to use a complex system of punches. And we have one die, but we can have different punches in the top part and in the bottom part, in order to assure the same density in the different levels of the part. Here we have one real example in a 4-stage compacting double gear multi-pattern adapter press from doors, in which to produce to this double gear with different levels in the part, we can assume with different punches on the top part of the die and in the bottom part of the die, we can assure applying the similar pressure in all the powder. We can adjust the density, the homogeneous density in the whole part. This homogeneous density is good for the next step, which is sintering. Just to mention that we can improve the density of these materials using the so-called one compaction process. In that case, we heat up a little bit till 110, 120 centigrade degrees the powder, and also we can heat also the die, the wall of the die. And in this case, we reduce strongly the GF strength of the powder, and applying similar levels of pressure, we can reach much higher levels of density. We can say that, for instance, using a conventional press system without heating the powders, we can reach 6.6, 6.7 grams per cubic centimeter in the green part, but using one compaction process, we can reach the order of 7.1, 7.2. So we increase a lot the green density, even giving the option, the possibility to the green machining, which is a good advantage. So after that, we have prepared the press part, and we have to go to the next step, which is the sintering. Sintering is produced usually in different kinds of furnaces. The most common furnace for the steel business, or even for the copper-based materials, are the so-called continuous furnaces, and the most extended one is the belt furnace. Also, if we can reach higher temperatures than are obtaining in the belt furnace, in the order of 1150 degrees, if we want to go to 1200 or even 1250 degrees, we have to go to the so-called walking beam continuous furnaces. In a continuous furnace, we used to divide the furnace in 3 different zones, in 3 different areas. The first one is the waxing area, in which we have to eliminate the lubricants that we have used to increase the compressibility in the powder pressing. Also, we have the area of the sintering, in which we can reach the highest level of temperature just to achieve the final density in the material, and as a consequence, the final properties. And we have at the end a large cooling zone in which we decrease the temperature, but also in some cases we can take the profit of this area using water jugs, trying to cool down the temperature in a fast way, and we can produce not a full quenching, but we can produce a rapid cooling in order to have some non-equilibrium microstructures and improve some of the properties. So, of course, we need other kind of furnaces. For instance, for the cemented carbide industry, it's normal to use different kind of furnaces. In that case, batch furnaces, in which we can control better, in some cases, the atmosphere, the temperature, and even we can introduce in the furnace different kind of gases depending of the step of the sintering. So both kind of furnaces can be used, but the first one, the continuous furnace, is most extended in the iron-based and copper-based industries, and the batch furnaces are more extended for the cemented carbide industry. So after sintering, of course, we can perform some heat treatments or some sizing and other treatments in order to finalize to get the final properties in the part and to reach the properties that we need for some specific part. So just for finishing, some transparency in order to to explain why powder metallurgy in the present sinter system are so extended in so many manufacturing of so many parts. So the first thing is just to give some energy considerations. So powder metallurgy is the cheapest way in terms of energy to manufacture metallic parts. If we compare the amount of energy that we need to manufacture 1 kilo of parts by machining, casting, or forging, or powder metallurgy, we need in some cases half of the energy than we need, for instance, in the case of machining. So this is just energy consideration. But today that we are living in a green planet, we try to live in a green planet. The use of raw materials is a very important issue. So, and if we consider the raw materials utilization that we have in present sintering, and we compare it with casting, extrusion, forging, and of course machining. In machining, we can lose in the order of 50% of the raw material. In powder metallurgy, usually we can lose in the range of 5–10%, and we can reach sometimes 20–25%, but this is not normal. But if we compare with the other processing methods, the utilization of raw material is much higher in the present sinter method than any other alternative in the metallic field. So, and just my last slide is just to analyze how is the market in terms of production in kilotons at least in Europe. If we compare the different methods to produce parts by powder metallurgy. In Europe, it was 2016 figures. In Europe, just 1% of the parts were produced by metal injection molding. The industry of hot isostatic pressing or materials produced by hot isostatic pressing is in the order of 6%. Hard materials, which combine press and sintering with other methods like also metal injection molding or hot isostatic pressing or other methods, is in the order of 6%. Non-ferrous materials like copper-based materials for bearings and so are in the order of 6%, and the present sinter of ferrous powder metallurgy is in the order of 81%. So if we consider the non-ferrous present sinter, the ferrous present sinter, and some hard materials, maybe we can reach the 90% of the PM parts produced in Europe are produced by present sinter. So I have tried to adjust my time to 20 minutes, so I did it, and we don't have time for questions, but I think I know that at the end of these three presentations we have some time for some questions, and I will be really pleased to answer any doubt that you can have after my presentation. So thank you very much, and I wait for your questions at the end of these three presentations.
Thank you, Jose. Yes, exactly. The questions will be posed to you after the end of all presentations. So please, everyone who has questions, please put them in the chat. Okay, so it's easier to find them later. But at the end, you can also raise your hand if you want. Now it's a time for the second presentation of today, and it's a time for Alberto Molinari of University of Trento, and he will talk about the properties of the materials press and sinter. Thank you, Alberto. Your floor is yours.
Thank you, Bruno. Can you hear me? And can
Absolutely,
you?
Yes.
Okay, everything is okay. Good morning, everybody. It's my pleasure to contribute to this seminar, speaking about the properties of the press and sinter materials. Let me use. Okay, the properties of materials depend on the chemical composition and on the microstructure. And if we observe the microstructure of typical press and sinter steel, we can observe the peculiar characteristic of this class of material, that is porosity. Pores are the black regions in this micrograph. The voids. Sorry? The void, something wrong?
No, it's okay. Yeah, I think someone.
The voids between the particles can.
Alberto, your micro is switched off. Alberto.
Okay.
Now it's okay. No,
now it's okay.
Now it's okay.
Thank you. So I don't know when. Okay, I go back to describe the image of the microstructure of the present sinter material. We have a residual porosity, the black regions, since the pores cannot be completely eliminated during the compaction and the sintering processes. And this slide shows that only a few properties do not depend on porosity. Those are the properties that depend only on the crystalline lattice of the material. On the other side, all the mechanical properties, all the physical properties, the surface topography, the response of present synthesis to heat treatment and surface treatment, as well as all the technological properties, for instance, corrosion and wear resistance, depend on porosity. I highlight in this slide the hardness. This is real hardness. Real hardness is the hardness we can measure using a low force in order to produce an indentation that doesn't involve porosity, pores in the deformed area. So this is the real hardness of the material. It doesn't depend on porosity. On the other side, we call apparent hardness the hardness we are measuring with a high force, a large force to involve pores in the deformed area. So let's start with some definition. And porosity is the main characteristic of the microstructure. This slide shows three different steels. Is the same steel, but was processed to obtain three different density, and you can observe not only how the pore fraction decreases or increases in density, but also how its morphology evolves and becomes even more rounded on increasing the final density. Porosity is defined by this equation, where ρ is the density of the material and ρ0 is the density of the pore-free material. But in addition to the amount of pores that can be expressed in terms of percentage or fraction of pores, we have other characteristics that have to be taken into account. First, the open or closed nature of porosity. That means open porosity means the pores are almost all interconnected. Closed means that the pores are isolated. And this figure shows that there is a threshold corresponding to about 5 to 7% of porosity. Below this level, pores are completely closed, isolated. Above this threshold, we have almost interconnected porosity. Moreover, we have to speak about the morphology of porosity, since it's strongly affecting the mechanical properties. To describe the morphology of pores, we may use the image analysis techniques, and the most used parameters are roundness and smoothness, that are defined by these two equations, where d min and d max are the minimum, the maximum ferrite diameter of the image, while A and P are the area and the perimeter of pores. Moreover, we have to define the size of the pores, and usually we adopt the equivalent diameter parameter that is defined by this equation. So let's start to speak a little bit about mechanical properties, and this is the most common way to show in a general way the influence of porosity on mechanical properties. In this figure, we had the yield strength, the elastic modulus, the tensile elongation, and the impact energy measured with the Sharpe test, normalized to the same property determined for a pore-free material, depending on porosity. And we may observe that all these properties decrease or increase in porosity, but we have to distinguish, since the influence of porosity is not the same for all of them. We can clearly see that the influence of porosity is much higher on toughness and ductility than for strength. And this can find a justification in the base deformation mechanism of the materials. I will try to explain a little bit in the next slide. But what is also important is that this is quite a common way to show the property of materials as depending on the porosity, but it's not completely right, since there is another important parameter. In other words, the mechanical properties do not depend only on porosity. This figure clearly shows that, for instance, the tensile strength of plain iron decreases on increasing porosity, but for the same porosity, we have that the UTS of the parts sintered at 1250 Celsius degrees rather than 1120, that is the common sintering temperature, the tensile strength is significantly higher. So it means that the mechanical properties do not depend only on the amount of porosity, but this difference is due to the different pore morphology we may obtain by changing the sintering temperature. So it's better to describe the mechanical property which with reference to all the parameters that affect it. Just a few words to explain the influence of pores on the mechanical property. Why we observe such a decrease in mechanical property? The reason can be understood by observing these two micrographs. These two micrographs are the results of in situ characterization of the tensile specimen on doing the tensile test. You can recognize the same pores in the two images. So the images are taken from the same region. This is the image at the beginning of the test, and this is the image when we reach 4% of tensile elongation, means we are in the plastic field. And you can observe that in correspondence of the pores, and in particular of the edge of the pores, we have some small cracks and some deformation that is promoted by the pore. And this figure better shows that we have cracks. This is a micrograph taken from a fracture specimen. We have cracks nucleating in correspondence of the pores, this one, and connecting to pores, pores. So it means that we have a stress accumulation in correspondence on the pores. And this is clearly described since more than 1 century. If we consider a pore like a discontinuity in the matrix as it is, and we may represent it as a lattice, having these two parameters, C is the semi-length and rho is the curvature radius at the pore edge, we know that in this region, when we apply a nominal stress sigma n, we have a local stress sigma L, which is much higher. And the correlation between the local stress and the nominal stress is given by this equation proposed by Inglis in 1913, so more than 1 century ago. So thanks to this, we have a local stress rising. The deformation is particularly strong in this region, so we have a localization of deformation, and we will reach the condition for plastic deformation and, in case for fracture, in particular in this region. So this means that we have localization of damage in this region. Of course, on increasing the stress, the area of this region expands, but nevertheless is not so easy to distribute deformation through the whole volume of the part. And this is the reason why the mechanical properties are lower than those of the corresponding pore-free material. All these phenomena depend on the pore morphology, and the pore morphology may be increased by the sintering temperature, as I shown in the previous slide. In case of fatigue, there is an additional parameter affecting the mechanical properties, the pore size. This figure shows a detail of a gear that failed under fatigue, and we may observe the fatigue crack nucleated in correspondence of this large pore on the surface. We know that crack nucleation occurs mostly in correspondence of the larger pore, the larger pores. We may also observe the crack nucleation in correspondence of the cluster of pores, but this is less common. What is most likely is that the porosity, the crack nucleates in correspondence of the larger pores on the surface. And the importance of the larger pores can be observed on this figure that was proposed by colleague Berkman during a seminar a few years ago, the fatigue strength of these two materials, they are material having this chemical composition plus carbon, of course, sintered at two different temperatures, can be put in a very nice correlation with this parameter, where HB is the hardness of the material and lambda is the effective length of the pore. So there is a clear correlation between the fatigue resistance and the size of the pores. On increasing the size of the pore, the fatigue strength decreases. And this correlation, even not so nice, so perfect, but is good enough, was also shown years ago by Professor Weiss and his colleague in work where they were investigating pure iron produced with different raw materials. So these results clearly indicate that the fatigue resistance is not only affected by density, by porosity, and by the pore morphology, but also by the size of the largest pores. Once the crack nucleates, it will propagate through the pores. I would say not quite easily, but there isn't such a big resistance to crack propagation as in case of the pore-free materials. So some examples about mechanical properties. I'm reporting tensile properties. In this slide, I'm showing the properties of two different steels. This is quite a common steel produced by adding carbon as graphite to a pre-alloyed powder containing 1.5% of molybdenum, and the final microstructure is bainite, is upper bainite. On the right side, the properties are relevant to a more alloy material. This is widely used in PM, obtained by adding 0.5% carbon to this powder, ferrous powder, where nickel, copper, and moly are added with a diffusion bonding system that has been mentioned by my colleague Jose Torralba in his presentation. In this case, the microstructure is very complex because it contains perlite, bainite, martensite, and nickel austenites. So the processing conditions to obtain these specimens are reported on the slide, and the source is the organized handbook for sintered components. We have 4 diagrams for each material. This one deals with the dimensional change on sintering. It's not important to discuss it. What I want to discuss is the yield strength, the ultimate tensile strength, and the tensile elongation. So these properties are reported as a function of density, or moving from the left to the right, density increases and porosity decreases, of course. And we may observe the positive effect of density on all the properties. We may also observe the slight but not but significant increase of the properties by increasing the sintering temperature. That has a positive effect on yield strength, on UTS, and on tensile elongation as well. In the case of these materials, we may find again the positive effect of density, the positive effect of sintering temperature on yield strength and on ultimate tensile strength, but in tensile elongation on sintering at higher temperature, we also have a decrease. And the reason for that is due to the particular constitution of this powder. On increasing the sintering temperature, we have a better diffusion of the alloy elements in the material, and the final microstructure contains more martensite and bainite than nickel austenite. That is the constituent providing ductility. On observing this figure, you may have an idea of the mechanical properties we may obtain. We may reach with these two materials, but there are a lot of materials with similar mechanical properties and even higher, but we can get yield strength from 300, 400 megapascal up to 600, 700 megapascal, 800 as well. We may reach tensile strength up to 1300 megapascal and tensile elongation in the range of 1 to 3%. I want to comment this last number just to tell that even if the tensile elongation is not so high, in comparison, for instance, to the tensile elongation of forged steel with a similar strength. In that case, it could be 6, 7, 8%. Even if it's not so high, it doesn't mean that the material have a brittle behavior. So these steels, they have a ductile behavior, as might be expected from the microstructure. The reason why tensile elongation is not so large is because it's very difficult to let the deformation spread over the wall of the cross-section of the wall of the material, as I mentioned before, showing you the microstructure with the damage localized. All the properties I showed before were relevant to sintered material. Mechanical strength may be increased by using all the treatments and operation we have in the steel technology. For instance, the mechanical strength may be increased by through hardening and sinter hardening. In this case, we have to take into account that the hardenability depends on porosity. This figure compares the geometric curves of the full dense material and of almost the same material with an increasing amount of pores, and we may observe that the geometric curve shifts towards left on increasing porosity. We may also use thermochemical treatments like carburizing and nitriding. In this case, we have taken into account that the case depth may depend on porosity, but there are well-developed technologies in order to control almost perfectly the case depth, as this figure shows. This is an image of a gear that has been low pressure carburized, and the case depth is very homogeneous and controlled along the wall of the teeth profile. Moreover, we may use shock peening. Shock peening is very interesting to increase, in particular, fatigue strength. In this case, we have to consider that shock peening may also give some surface densification that will contribute to increase the mechanical fatigue strength, adding its effect to that well-known resulting from the residual stress. We may reach the same level of residual stress, compressive residual stress on the surface we obtain on forged steel. Just a few words on some physical properties, also important since present sintered materials are not used only in structural application, but in other applications where, for instance, magnetic properties are required. To speak about magnetic properties, it is important to make reference to the typical magnetization diagram, where on the x-axis there is the magnetic field, and on the y-axis there is the magnetic induction. So the most important parameter to describe the magnetic properties are the permeability, that is the slope of the first run, then the maximum induction, the coercive force, and the magnetic loss. That means this hysteresis, the area of the hysteresis area. And with the present sinter technology, we may produce several soft magnets characterized by the low coercive force, starting from iron, iron phosphorus, iron silicon, iron nickel, iron cobalt, and very special products, soft magnetic composites, where the single iron particles are coated by a very thin isolating layer that remains in the final microstructure, improving significantly the magnetic properties. Just to give you a synthetic overview on the magnetic properties, we may say that on increasing density, density affects all the properties I mentioned. So on increasing density, we have an increase in induction, in permeability, in the coercive force, but we have a decrease in magnetic losses. The sintering temperature, with its effect on the pore morphology, increases permeability, coercive force, and decreases the magnetic losses. We wish to control carefully the content of impurities, in particular resulting from interaction with the sintering atmosphere. The low amount of impurities affects the properties as reported, as indicated by the arrows. And finally, the grain size. So This figure shows the influence of the characteristic and the processing parameters in indirect influence of the processing parameters on the magnetic properties. A few words on thermal conductivity. Thermal conductivity is quite a complex characteristic that is the combination of the thermal diffusivity, the specific heat capacity and density. This figure reports the results of a paper from Professor Danninger in Vienna, where the specific heat capacity and the thermal diffusivity are reported as a function of temperature for this material preset sintered to different densities. And we may observe, as we may expect, that the specific heat capacity doesn't depend on density, while the thermal diffusivity, of course, depends on density. It increases on increasing density. As a consequence of that, the thermal conductivity has a strong dependence on density, as reported in this final diagram. The last properties I want to show is electrical conductivity. Again, I'm making reference to a paper recently presented by Momeni at our Congress in the World Congress last month. Here, the electrical conductivity is reported as a function of density or porosity for three different steel. A carbon steel, Fc, this point, high alloy steel, DC, DC are these points, and the one less alloy steel, MC, the other point of the figure. And all these steels have been sintered at two different temperatures. We may observe that the thermal electric conductivity increases on increasing density. The influence sintering temperature is not so much pronounced. And by plotting the electric conductivity versus total porosity, it's possible to draw some models, some equation that can be used in the prediction of this property. So, to conclude my presentation, mechanical and physical properties of the present material depend on density porosity, and of course on the microstructure. The porosity, I show you, that causes stress rising and strain localization, and as a consequence, the mechanical properties are lower than those of the corresponding materials pore-free. The influence of porosity may be attenuated by improving the pore morphology, and the best way is that to sinter a high temperature and by decreasing the maximum pore size, and this is in particular important for fatigue. The property may be The sinter property may be further increased by heat and thermochemical treatments or mechanical surface treatments, and the response of the material to this operation depends on porosity, are affected by porosity. We may obtain with the present sinter family and material family quite a broad range of mechanical properties. Also, the physical properties depends on porosity and density, I have shown, but they also depend on impurities, and it is very important to control the impurity content during the process. What's important to recognize is that all these effects are well known and well assessed. There are several reliable models that correlate the properties to porosity density, and these models can be used to predict the behavior of the porous material. And as a consequence of that, I would say that PS present sinter porous material are a very reliable alternative to the corresponding materials produced with other technology, also in terms of properties, even in demanding application. Okay, this was my last slide, and I thank you for your attention.
Thank you, Alberto, for the presentation on the properties. Of course, everything rotates around porosity and density. There will be questions in the question and answer, I'm sure. And now we have to switch to the last technical presentation of today from Arno Steyer from GKN Sinter Metals Bruneck. He is already there. I think he can share a presentation and give us his talk on the guidelines for design and case studies present sintered parts.
Okay, can you hear me?
Yeah.
Okay,
Fine.
great.
Hear and see.
First of all, thanks to Bruno and the EPMA team for inviting me to this webinar. It's a pleasure. Obviously, my presentation is not so scientific like from Professor Molinari, but I am pointing a little bit to the basics of press technology. Since we have not so much time, I'm trying to be fast. Just to recap of all the people not so familiar with the PM technology, a very simple compacting tool for a gear consisting of a die, 2 punches, and the so-called core rod in the middle. Just to have imagine how big is the press force to compact the powder from density 3 to 7 point something. You can imagine it's the same pressure from a small passenger car on a thumbnail. Here is shown very simply the conventional pressing cycle. You see here the die, the 2 punches, and the red one is the powder. Filled has an apparent density of 3 point something, and is afterwards compacted, let's say, to the half of the length, to density 7 point something. After that, the punch is going up or the die is going down in order to extract the so-called green part. And with the next filling step, filling sure the powder comes from above from the press, is filled again into the die, and the compacted green part is extracted. Let's show you a few non-feasible geometries with the conventional PM technology. This is, for example, grooves. These are undercuts, and if you remember that the part have to be extracted, you can imagine why undercuts are not feasible. This is another version of groove or undercut, not feasible. As well as radial bores. We are not able to compact radial bores. We are even not able to compact threads. And round shapes is, but some of them in my case study slides, I show you some creative examples how some of these hurdles could be overcome with the conventional technology as well. Let's tell a few words about the length of the compacted part. This is not unlimited, since due to the friction in the compacting tool, the density to the middle of the part decreases a lot. Take in mind 60 to 70 millimeters of part length. After that, I have so less density in the middle of the part, the so-called neutral zone. That's the green part is not the green density is too less in order to extract the part well. And this shows the density distribution in a part. Obviously, to the ends, I have the biggest density and decreasing to the middle of the length. This is shown two different geometries. This is two simple tools, a single layer part with the white neutral zone in the middle of the green part. And this is a double layer part with a step in the die, and as well here I have the lowest density in the middle of the part. This is a more complex tool, a multi-layer compaction tool consisting of 2 upper punches, a die, a core rod, and 3 lower punches. And as well here you can see in each single level the zone with the lowest density is always towards the middle. Let's speak a few words about the tool building. This is usually made with erosion. For example, the die is usually cut with wire erosion, and since the wire itself has as well a diameter or from 10 to 20 0.10 to 0.25 millimeters, my radii on the pad are not cannot obviously be sharp edges. So I have to consider seeing some of different gear geometries. Take in mind 0.2 minimum on tooth tip or tooth root or even inner splines of minimum radii. If you are seeing a customer drawing from a gear, 0.2 minimum radius to consider. Yeah, let's speak a few words about the burrs with the conventional technology. You can imagine all tool components have to move into each other, means the two punches are moving into the die and the corrode into the punches. And you can imagine that all the single tool components need a minimum of clearance, take in mind up to 30 microns of clearance between the different tool components in order to move without friction or wear. This leads to a very thin burr on the compacted green pads, which in some cases the customers or for the function might not be useful. And obviously you can deburr the pad afterwards with tumbling or something like this, but on gears especially, tumbling causes nicks and dents and is not maybe the right process. So you can adopt a few tricks, let's say, especially on gears here shown. You can move the burr down from the functional plane. Let's say for gear, this would be the bearing or the actual bearing functional face, and this is a fixed step on the upper punch, and I have the burr here lower than the functional plane, and I don't need to deburr. I can realize these chamfers on the punch like this, circumferential, and I have the burr here under this plane, so no burring is needed. And this is a third method. As you can see, the burr is as well under the functional surface. A few words to the fixed steps on a compaction tool or on the punches. Some geometries need to have fixed steps on the punches, since the punch cannot be divided. They would be too thin or too small. So if you follow the following rule, first of all, you need on the fixed steps some draft angles or some radii. Otherwise, after the extraction, it doesn't go out well of the tool. And the fixed steps can be realized up to a length of 0.1 to 0.3 of the total part length, depending obviously always on the density, on the total density. You can realize fixed steps on the punch without having issue of too much density. Minimum wall thickness on pads. This is as well not unlimited thin. Consider towards to the die a minimum of 1 millimeter of wall thickness, and to the inner punch of 2 millimeters. Why this? You can imagine with that pressure in the first slide, we have lots of forces on the tool. The tool is going to deflect, and if my punches are too thin, they are going to break. This example shows a customer pad with two levels. As you can see, a longer inner hub and three vanes built from a second punch, the blue one. This was the initial customer design, means the inner one is the green punch and the blue one is the outer punch. This is way too thin for a punch geometry. This would immediately break down. So the engineer convinced to optimize this blue punch to this geometry. I have here an angle of about 90 degree. 90 degree or bigger is always good. So the tool is not breaking. Tools, if you consider, are made from very hard materials. This just to show that even helical compaction is possible with different concepts and different geometries. The punches obviously have to turn into the die, or one punch is turning at one die. I don't want to go too deep in detail on this since we don't have so much time. Let's speak a few words about the tolerances. They are not identical in the compaction or axial direction or in the radial direction or tool direction. As you can see already in this slide, you can imagine that in axial direction we need much more tolerance, since I have much more tool components and much longer tool components which are deflecting and having then a spring-back behavior affecting my length tolerances. In radial direction, the tool is much more stiffer and I can realize closer tolerances. These are some guidelines with different densities and lengths, but take in mind plus minus 0.1 is always a good starting value for length tolerances if you are having or studying customer drawings. Obviously, on smaller parts and with more precise presses, you can realize even a little bit smaller length tolerances, but 0.1 to 0.2, this is the limit without any secondary machining. Okay, let's talk a few words of sizing. As you already have seen in the previous presentations, we have the compacting, and after the sintering, obviously I have some deformation on the part. And for that reason, a very common process is the sizing. The sizing tool is obviously similar to a compaction tool, but much more simple. If a compacting tool with a part of this geometry needs 3 lower punches, 1 upper punch, the sizing tool has a stepped die, since I don't need to densify each level once again. A core rod and an upper punch and a lower punch. So it's simpler than the compaction tool. Why do I need sizing? I need sizing for optimizing general and partial tolerances after the sintering, when the part gets deformated. If I need to straighten the parts, obviously even the flatness and the planarity is getting worse after the sintering, so I can re-improve. If I need to re-densify, as we heard in the presentation from Professor Molinari, in order to get more strength. If I need smooth surfaces, it's very common on the sintered bearings for having smooth surfaces, and I can realize some special geometries like radii or chamfers, surface contours with a kind of a coining, you can imagine. This is an example. The compacted part has this geometry, but I need just a tight tolerance on this bore and this inner diameter, so the sizing tool obviously have not the complete shape, but just 2 round punches, and so I can do a partial improvement of the 2 bores. This is an example. Again, I have a compacted part like this, and the tight tolerance is needed just on the inner diameter, so obviously I don't need all the small core rods, but the sizing tool has just the lower and the upper punch and the precise inner core rod. This is a very thin pad, and in this case it's getting oval or deformated after the sintering, so I need to size the pad with a round sizing tool in order to have the cylinder form or the runout improvement after the sintering. This is an example from a very thin pad with a tight planarity tolerance. In this case, I can press on the pad to improve the planarity again after the sintering. And in this case, I use the sizing to densificate the part, to make it smaller than the compacted and sintered pad in order to get more density and more performance. Just some picture of the surfaces after the sintering. You can see on the left hand side, and after the smoothing of the sizing on the right hand side, so you can imagine that this surface works much better on bearings and functional surfaces. And speaking from tolerances, keep in mind tolerance grade 9 we just pressed and sintered pads. And if I go into size, always speaking from the radial direction, I can realize tolerance grade is from IT7. Okay, this leads to some case studies. Design for PM. Design for PM. Design for PM is a kind of a mindset, means the engineer should always trying to understand what is the custom application. Very often the customers come with non-feasible geometries, like we saw in the second slide. But understanding the application, in much cases we can propose a geometry which is feasible with our technology and does the same function or even better. Let's start with this example. This was a very small part, as you can see here on this illustration, and it was a kind of a nozzle with radial bores. Sorry, as we saw in the first slides, this is not feasible since I cannot extract. This part had the function of some gas flow, and converting this geometry from the customer to this geometry, we were able to have no radial bores again, and the part had the same function, and were easily able to compact with the standard technology. Next slide. This is a shock absorber pad, very common pad for the PM technology. As you can see, as you can see, here are some oil channels. This would be even not this cannot be realized even not with machining. So what was the creative PM solution? Compact two single pads in compacting, and in the sizing operation to join them together to one pad and having this oil channel geometry after the sizing. This is one of the most beautiful examples, in my opinion, where our conventional technology can give to the customers added value. Here the initial design was 3 single pads from the customer, 2 gears and the third pad all joined together, and with a few optimizations on the geometry, we were able with the customer to convert these 3 pads together to 1 single pads compacted in 1 single step, and you can imagine which was the added value and the cost improvement for the customer in this case. This is a very nice example where we overcome the undercut technology with for the so-called mirror plates. They are used to attach the mirror onto the windscreen, and with a special tool concept, we were able here even to compact this with the undercut, and then it was extracted not to the upside but to the front side, and so we overcome this limitation as well. This is an example where is seen in the presentation of Mr. Tovalba. Main bearing caps in the engine. In Europe, unfortunately, this is the standard technology, I would say, is die cast, but in the US market, the standard is already PM technology. You can imagine if you use the die cast technology, they have to be cut first in single parts and after that machined. And if you use PM technology, you can already compact them with weight optimizations and in a single part. We started now with a few custom applications and hope to increase the market share even in Europe. Another example where the camshaft is from a die cast, fully machined cam lobes, and with the PM technology we can compact every component's single parts, and after that they are fitted onto a tube. Even there an added value for the customer with our technology, very precise. This is as well a very good example and a very common technology now in automatic transmissions, in first instance in China and in US. These so-called planetary carriers, standard technology, die cast and everything machined, very, very big parts. In this geometry, obviously none to be realized with the conventional technology, but there is a so-called brazing technology. Means I am going to compact 4 different PM parts, and then before the sintering I put them together, and with some brazing material or brazing pins, I think they're made from copper, I can sinter all the single parts together and need maybe just the machining of some precise holes and not from the complete geometry. So very nice example as well. We heard as well from the sintered bearings. In this case, an advantage is I don't have to machine or I don't have to press the bearings completely centric. Means on an electric motor, I usually have 2 bearings. One is a cylindrical one, and the second one in this case was an eccentric one in order to compensate the actual misalignment, and so I can compensate some errors on the housing. This is an example. We saw as well no threads feasible, but there are as well technologies where we can feed a full steel part, in this case some pins or small threads into a PM part in the compaction process, and then after the sintering they are being sintered together in order to realize such parts with undercuts or threads. This is a can phaser or VVT part, as well very common PM part, and they all need radial bores for oil channels. This is done usually by green machining, and this was a nice concept to eliminate this green machining with a compaction of 2 single pads like this, and then put them or fitting them together and having these radial holes without any green machining. This example is as well very standard now in the combustion engines, is the so-called variable oil pumps for the engine lubrication. This oil pump always have the similar oil flow in order to optimize the emissions with an eccentric setting ring, a rotor, and the PM vanes. The PM vanes in the past were made from sheet metal, full steel, with heat treatment and fine grinding, but we were able to convert this into full PM vanes. They are just pressed, sinter hardened, and deburred, and so we don't need any fine grinding as well here. We are delivering millions of the pads each year. Nice example. And last but not least, one of the most beautiful examples in my opinion. This is an electric pump for a double clutch transmission, a very famous one. We have 3 of these small pumps in the transmission, 2 for the clutches and 1 for the lubrication. The customer came to us with a full machined aluminum housing with the housing and the cover, and here the PM G-Auto set, and we were able, together with the customer, to convert this in a full PM pump. No machining needed anymore, just a grinding, since hydraulic pumps has very tight tolerances for the efficiency, but no milling, no turning. And besides the cost effectiveness, with a full steel pump or PM steel pump, you can imagine I have always the same efficiency, since the thermal expansion of steel and aluminum are different, and on a full steel pump I have always the same clearance, even on minus degrees or plus 100 degrees for the operating fluid. So I am at the end of my presentation. Thank you very much for your attention, and I'm happy to answer to your questions after the session. Thank you.
Thank you, Arno, for your presentation. I think it was interesting to see case studies from one of the most important PM producer in the world. So I guess it's time for the questions and answers, as you already mentioned, and we have some questions in the chat, but of course you can also raise your hand if you want to ask. We're a bit late today, so let's try to go straight to the questions. I go to the first. I think it's for this was for Jose actually. There was a question from Marco Pallini. What about AM usage in Europe? You're muted. You're muted, Jose. Sorry.
Now you can hear me. So
yes.
Sorry for that. I was thinking in the conventional press and sintering technologies, AM has emerged in the last few years, but maybe Bruno can help me to answer, because in my opinion the real production of AM in terms of tons in comparison with press and sinter parts is negligible. It's not so high in comparison with the. Of course, it's an emerging technology that in the future will really boost on the market, but today is still more at the labs and in the research developments, but not in the real PM part production. Is in terms of a lot amount of tons. I don't know. You have to say something, Bruno.
Yeah. I don't have the figures offhand now, but normally in our surveys it comes up that AM is increasing, as you said, still barely visible in the pie chart that you showed. Yeah. So something like 1% maybe of the total market. That's because there's a lot of work, as you said, in the research and development, but also because of some capacity limitations of the technology in terms of speed and number of parts that you can produce in a given time, there is no huge production yet. So
under the point of view of the university people and the research centers, it's amazing because it's a booming effect now in the research field. There are a lot of people working on that, and I suppose that in a few years there will be a lot of applications in the industry. But by today, it's still a very small amount of tons.
Right. Second question from Alicia about warm pressing. What would be the recommended temperature for warm pressing?
I am not an expert, but I have read a lot about warm pressing, and in my opinion, it's in between more than 120, 140 than 100. It's more near to 120 than to 100. So, and today the tendency is not to warm the powder, it's just to warm the dies, more than to warm powders and dies.
Okay. Yeah, then if we browse down, let me check. Okay, so there's another question from Cash. That's for Alberto Molinari. So if you could explain again the relationship between density and hardenability and the reasons behind.
In 2 minutes,
yes.
Alberto. Don't
In
use
2 minutes is
don't use 1 hour.
On 1 foot.
No, but this is very good question. Okay, in principle, the main reason is that on increasing density, thermal conductivity increases, and therefore the cooling rate in the internal layer of the part increases on increasing density, and we may achieve more martensite in depth on increasing density. This is the reason. The geometry test gives some, I would say, sometimes some wrong results. So it's not really the best way to understand the influence of density on hardenability, since when we measure hardness in the geometry bar, we have the influence of density on hardness. So for the same microstructure, in a region where we have, for instance, 80% of martensite, the hardness that we are measuring depends on the local density. So the geometry test enhances the influence of density, since there is the contribution of density on hardness. The best way to understand hardenability should be to measure the martensite content in depth. And don't forget that we are in a geometry test, we are using hardness to determine the martensite content. It is much easier doing it by hardness than doing it by the optical microscopy, for instance. But the best way to eliminate the influence of density on hardness should be that of measuring the martensite content. Nevertheless, in conclusion, on increasing density, thermal conductivity increases, and therefore the martensite transformation can propagate in depth in the part. Okay,
I hope that answered. Another question, I don't know, maybe also Alberto. Can parts with porosity be considered for bearing applications, or is it essential to process pore field structures? What is the criteria? How much is the accepted porosity level? I think we can answer yes.
Yes,
we have
sure.
porous bearings.
I think that the self-lubricated bearings are perhaps one of the oldest products in the present sinter technology. The porous bearings are infiltrated by oil, and then the oil is delivered during the use of the bearing in the contact region, drop by drop, I would say. In this case, it's very important to design porosity because there is an optimum distribution, amount of porosity, and an optimum size of porosity in order to avoid that either impregnation or oil delivering doesn't work properly. I'm not expert in the design of porosity of self-lubricated bearing, but I'm sure that porosity is, in that case, porosity is very important characteristic of the material. I would say more than the bronze that is the constituent of the bearings. The answer is yes, for sure.
Yes, I have to say also that the porosity here is an advantage. It's not a drawback. It's a real advantage. Yes. You need the porosity to have the self-lubricated bearing, and this porosity should be open porosity. So that means higher than 12, 14%.
It's a functional phase, I would say.
I'm sure that Arno Steiner could tell us how many millions of bearings or self-lubricated bearings they produce every year.
Yes, billions, I would say.
Billions, okay, yes. Billions.
Billions.
Maybe there's another question just for Arno here, a bit tricky. Comes from Hank. How much will the PM market for automotive parts shrink due to electrification? That's a tricky question to answer.
Nice question. Nice question. Yeah, and yeah, obviously it's a realistic question. We hope that that the PM content will not decrease so fast. I studied some market studies, and this showed me that okay, the conventional combustion engine goes down. But on the other side, the hybridization goes up, means we have smaller engines in the future, but the smaller engines are even more complex, means they need more balance weights, VVTs, in order to have the good emissions. And that is my hope, that the conventional engine is not completely disappearing. Obviously, in electric car, yeah, the conventional engine parts disappears, but seeing from the current point of view, I personally don't believe that this is being so fast that the conventional engine will going to disappear. This is my personal feeling, and I personally hope that even hydrogen combustion in a conventional combustion engine could be a future option. Yeah, but obviously everybody now is fearing from the electrification. And yeah, even if we know that an electric car hasn't lower emissions than a combustion car currently, but yeah, that's the realistic point of view. Scheffler told that if now everything is changing to electric cars, the emissions will increase, not decrease in the next 10 years. But yeah, we are fighting against this behavior.
Yeah, I guess that mainly depends on the way the electricity is produced. And let me give some advertisement again. We have a seminar on this in 1 month. So if you're interested in this topic, you can join the seminar next month.
No, but just to conclude, I think hydraulic pumps, like we saw on the last slide, is still needed for lubrication, cooling, and so on. I think aluminum maybe for heat sinks and so on could be an opportunity. We have to change completely the mind, I think, with electrification.
And there's more room for magnets, soft magnets, hard magnets, all produced by PM.
Or small motors, right?
Okay, another question for Alberto. In your experience, what is the depth, but maybe also for Arno, the depth affected by shot peening, and what is the density improvement starting, for instance, from 7.1 grams per cubic centimeter part?
Of course, the depth depends on the yield strength of the material. Just to give some numbers, the densified layer on the surface about 30-40 micrometers, no more, and the density may be up to 7.7 or something like that. So in principle, you may completely eliminate the residual porosity. What is even more important is the depth of the compressive residual stress layer, and this is around up to I would say 100 micrometer, no more. Unfortunately, the surface densification uses part of the energy we are delivering to the material. And this means that the energy used to densify the surface is lost in terms of residual stress. This is important to understand. And another very important point is that the surface densification, okay, could be positive because we are increasing the mechanical property of the surface, but it is the result of deformation of the part. So we may have some worsening of the surface profile of the surface topography. Just to conclude, my feeling is that by shot pinning we shouldn't try to add the maximum surface densification as possible. Better to maximize the residual stress profile and using very controlled shot pinning, perhaps using ceramic shots and not steel shots. But this is my experience and my personal opinion.
There's another question on lubrication, self-lubricating applications. The pores are, the question is if it's correct that the pores have to be interconnected and not closed.
Yes, yes, of course. Yeah, it will be open and interconnected.
Yeah, so density has to be low. Good. Yeah, I think that's more or less the questions that we have in the chat. I have only one other question for Arno about sizing. What is the impact of sizing in terms of added cost to the process of producing the part? I mean, of course, it cannot be generalized, but is it comparable to the pressing that you have? To the sintering, which is the impact?
I would say from the tool cost perspective, as you have seen, it's a little bit more economic. And speaking from the process cost, I would say it's comparable to the compacting, maybe a little bit more economic on bearings, because we really have high speeds on the sizing, and we are going to size two parts together in one stroke. But I would say almost comparable.
Yeah. Okay. And also, I was seeing your first slide where you said no radial features are possible, but I know you have industrial applications where, of course, you have special processes to do that. So I don't know if you want to comment on that.
The colleagues from Bonn are very creative on developing very complex compaction tools with even overcoming the limits of the conventional technology.
Yeah. So good. So I hope we have shown you that there are many opportunities in powder metallurgy, even in the old conventional press and sinter, which is still evolving even after, I don't know, 50 years of steady production. Yeah. Maybe we can take the final question, the final part of the session. I wanted just to ask you some more questions. So if you don't mind, I share my presentation again. If it works. Okay. So do you see my slides?
Not yet.
It's very slow. Let me do like this. So,
no.
Yeah, but I wanted to go here. Okay. So first of all, this was the map of registrants I wanted to show you at the start. So you can see it's worldwide. Thank you again. I don't know, I will have to do the same map for the participants, but thank you, Spain, especially. Also India and all the other countries are represented here. Thank you for being here. Last part of a session, if you can go again to Slido and choose this other event code, PSW 01, and then I will ask you some more questions. And let me go to that. Always very simple questions. So first question is just a summary of what we have shown you today, if you think that these are important, but also in the concerning sustainability of the parts. So if you think you've seen the energy considerations given by Jose and the material usage considerations given by Jose at the start. And as we are working on this side, and we will also have projects on this, it's important to know your opinion. It seems overwhelmingly on the yes side. So I hope, I think we have been convincing. Yeah, we don't have much time. We are already very late, so I think I will just move on to the next slide and ask you to comment on the other question, which is, so you've seen this webinar. I don't know, maybe not many of you were really not aware of what Present Sinter was able to do, but I would like to ask you if you have had some useful answers from this webinar. You could also answer that you're less confident in Present Sinter if your impression was negative. It's not the case. So good to hear, good to read, good to see. And then I would just move to the last question, which is very simple, and I would just ask you to give us a mark, a vote on what you had in this webinar. And again, thanks for joining anyway. This is nice to see as a feedback. So while you vote, I think I can start thanking all our speakers again. I will then go back to the main view while you still vote, and have the speakers on the screen again for the last thanks. So thanks in order of introduction to Jose, and to Alberto, and then to Arno, for all the interesting details you gave today. And well, thanks to all the participants.
Thank you to you also. Thank you very much.
Thank you.
Thank you, Bruno. Thank you, everybody.
Yes, and don't forget to check our website for all the next events. We hope that this was a good appetizer for what is coming in the next months and years. People are usually in powder metallurgy for many decades because it's addictive. So hope to see you many more times. Thank you very much for being here today, and have a nice day.
Bye-bye.
Have a nice day. Bye.
Stay healthy.